We live in a world where much of the most important and powerful forces that govern our existence are invisible to the naked eye. We may observe the results of these forces, objects falling to the ground, the movement of galaxies, or the bending of light, but the forces themselves remain hidden, working silently in the background. From the motion of planets to the formation of galaxies, these invisible forces shape our universe, dictating the way everything behaves. And while we take many of these forces for granted, we have only begun to truly understand them. In this chapter, we will introduce some of the most powerful and enigmatic invisible forces that shape our reality: gravity, dark matter, dark energy, and the electromagnetic force. These forces are responsible for everything from the formation of stars to the behavior of particles at the smallest scales. Yet, their full nature remains a mystery. How do they work? Why are they so difficult to detect? And what is their true role in the cosmos? Let's begin by diving into these forces, exploring their influence on our daily lives and the universe as a whole, and uncovering the hidden mechanisms that shape the world we experience. Gravity, the invisible force that binds the cosmos. Gravity is the most familiar of the invisible forces, and yet it remains one of the most mysterious. We experience gravity every day, when we drop something, when we jump and fall back down, or when we feel the weight of our own bodies pressing down on the ground. But while we understand the effects of gravity, its true nature continues to baffle scientists. The concept of gravity was first introduced by Isaac Newton in the 17th century, who proposed that every object in the universe exerts an attractive force on every other object. This gravitational force was shown to be proportional to the mass of the objects involved and the distance between them. Newton's law of universal gravitation explained how the planets orbit the sun, why objects fall to the ground, and why tides rise and fall due to the moon's influence. But while Newton's laws provided a powerful framework for understanding gravity, they did not explain what gravity is or why it works the way it does. The true nature of gravity remained a mystery until Albert Einstein's theory of general relativity in the early 20th century. According to general relativity, gravity is not simply an invisible force acting at a distance, but rather a curvature of space-time caused by massive objects. The more massive an object is, the more it bends space-time around it, creating what we experience as gravity. This curvature of space-time is what causes objects to move in curved paths, like planets orbiting stars or objects falling to Earth. One of the most fascinating aspects of general relativity is that gravity is not just a force in space, but a property of space-time itself. The fabric of space-time is distorted by massive objects, and this distortion dictates the way objects move within it. It's a mind-bending concept. Gravity is not a force acting across empty space, but the very nature of space itself being warped by the presence of matter. While general relativity has been experimentally verified in numerous ways, including the observation of gravitational waves in 2015, gravity remains an enigma. Despite its profound effects on the universe, scientists still cannot fully explain what gravity is at a fundamental level. In fact, gravity is the only one of the four fundamental forces of nature that has yet to be successfully incorporated into a unified theory of quantum mechanics, which governs the subatomic world. This is one of the greatest challenges in modern physics, understanding how gravity operates on both the large scale of galaxies and the small scale of quantum particles. Dark matter, the hidden mass that shapes the universe. While gravity is the force that governs the motion of objects, it is not the only invisible influence that shapes the universe. One of the greatest mysteries in modern cosmology is dark matter, an invisible form of matter that makes up about 27% of the universe. Unlike ordinary matter, which interacts with light and can be seen through telescopes, dark matter does not emit, absorb, or reflect light, making it undetectable by traditional means. So, how do we know dark matter exists if we cannot see it? The answer lies in its gravitational effects on visible matter. In the 1930s, astronomer Fritz Zwicky noticed that the galaxies in a galaxy cluster were moving much faster than they should be, given the amount of visible matter present. According to Newtonian physics, the galaxies should have been moving more slowly because the visible mass in the cluster was insufficient to account for their high velocities. Zwicky hypothesized that there must be some unseen matter in the cluster providing additional gravitational pull. This was the first indirect evidence of dark matter. Since then, scientists have found more evidence for dark matter's existence through its influence on galaxies, galaxy clusters, and even the cosmic microwave background radiation. For example, the rotation speeds of galaxies are much higher than what would be expected if only visible matter were present. The outer stars of galaxies, far from the center, should be orbiting more slowly if the galaxy's mass were made up solely of visible matter. However, they move at nearly the same speed as stars closer to the center, suggesting there is additional, invisible mass providing extra gravitational pull. Despite numerous observations pointing to the existence of dark matter, its true nature remains elusive. It does not interact with electromagnetic radiation, light, so it cannot be detected directly. It also doesn't appear to interact strongly with ordinary matter, meaning it likely does not involve the strong or weak nuclear forces. The most popular candidate for dark matter is a class of hypothetical particles known as WIMPs, weakly interacting massive particles. However, no experiment has yet successfully detected these particles. The mystery of dark matter has profound implications for our understanding of the universe. If dark matter exists, it plays a crucial role in the structure and evolution of the cosmos, influencing the formation of galaxies and clusters, as well as the overall dynamics of the universe. Dark energy, the force. Accelerating the expansion of the universe. While dark matter is the mysterious substance that holds galaxies and galaxy clusters together, dark energy is the equally mysterious force that is pushing the universe apart. Dark energy makes up about 68% of the universe and is responsible for the accelerated expansion of the cosmos. Unlike dark matter, which has a gravitational pull and works to attract matter together, dark energy is thought to exert a repulsive force that counteracts gravity. The discovery of dark energy was one of the most surprising findings of the 20th century. In the late 1990s, two teams of astronomers were studying the supernovae of distant galaxies to measure their distances. What they expected to find was that galaxies were moving away from us at a constant rate, consistent with the slowing expansion of the universe due to gravity. However, to their surprise, they found that the universe's expansion was accelerating, not slowing down. This unexpected acceleration could only be explained by the existence of a mysterious repulsive force, dark energy. Since this discovery, dark energy has become one of the most important and enigmatic aspects of cosmology. While we have evidence of its effects on the universe's expansion, we have little understanding of what dark energy actually is. One possible explanation is that dark energy is a property of empty space itself, a kind of energy that is intrinsic to the vacuum of the universe. This is known as the cosmological constant and was first introduced by Albert Einstein in his equations of general relativity. However, there are alternative theories that suggest dark energy could be a dynamic field that changes over time. Despite the many unknowns, dark energy is believed to dominate the fate of the universe. If dark energy continues to accelerate the expansion of the universe, it could lead to a scenario known as the Big Freeze, in which galaxies drift farther apart, stars burn out, and the universe becomes an increasingly cold and empty place. Electromagnetic force, the invisible force that powers the universe. While gravity, dark matter, and dark energy are the major invisible forces governing the large-scale structure of the universe, the electromagnetic force is one of the fundamental forces that governs the behavior of matter at the microscopic level. It is responsible for the interaction between charged particles and is responsible for a wide range of phenomena, from the formation of atoms to the behavior of light. The electromagnetic force is one of the most familiar forces in our everyday lives. It governs the behavior of electricity and magnetism, and it is responsible for the behavior of electromagnetic waves, including light, radio waves, X-rays, and gamma rays. It is also the force that binds electrons to the nucleus of atoms, holding matter together. The electromagnetic force is much stronger than gravity, but it operates over much shorter distances. It can be both attractive and repulsive depending on the charges involved. Like, charges repel each other, while opposite charges attract. This force is carried by particles called photons, which are responsible for transmitting the energy of electromagnetic interactions. The effects of the electromagnetic force are all around us, from the electricity that powers our homes to the way light interacts with matter. Yet, despite its ubiquity, the electromagnetic force is still not fully understood at the deepest level. One of the major goals of modern physics is to unify the electromagnetic force with the other fundamental forces of nature, such as the strong and weak nuclear forces, into a single theory of everything. Conclusion: the invisible forces shaping our universe. The invisible forces that govern our universe, gravity, dark matter, dark energy, and the electromagnetic force, shape everything from the smallest particles to the largest galaxies. While we have made incredible strides in understanding these forces, many questions remain unanswered. These forces operate on scales far beyond our everyday experience, and their full nature is still largely unknown. As our knowledge of the universe continues to expand, we will undoubtedly uncover more secrets about these hidden forces. The search for dark matter, the study of dark energy, and the quest to understand the fundamental nature of gravity and electromagnetism will continue to challenge scientists and inspire new discoveries. Ultimately, the exploration of these invisible forces will help us uncover the true nature of reality, providing a deeper understanding of the universe and our place within it. As we explore the universe, we begin to encounter some of the most enigmatic phenomena that, despite their influence, remain hidden from direct observation: dark matter and dark energy. These two mysterious components make up roughly 95% of the total mass-energy content of the universe, yet we can't directly observe them. They do not emit, absorb, or reflect light, making them invisible to the instruments we typically use to study the cosmos. And yet, without them, the universe as we know it would not exist. Their gravitational effects on galaxies, galaxy clusters, and the very fabric of space-time are profound, yet their nature remains elusive. In this chapter, we will dive deeper into dark matter and dark energy, exploring their roles in the evolution and behavior of the universe. We will discuss how scientists came to realize that these invisible forces must exist, despite the fact that they cannot be directly detected by our traditional tools. We will also investigate what we know and don't know about these forces, and how they might hold the key to some of the greatest mysteries in modern physics and cosmology. What is dark matter? Dark matter is perhaps the most famous of the invisible forces shaping the universe. It was first proposed in the early 20th century as a way to explain anomalies in the motion of galaxies and galaxy clusters. Although dark matter cannot be observed directly, its gravitational effects are clearly visible, and it is believed to make up about 27% of the universe's total mass-energy content. So, what is dark matter and why can't we see it? The first hints of dark matter came from the work of astronomer Fritz Zwicky in the 1930s. While studying the Coma galaxy cluster, Zwicky noticed that the galaxies within the cluster were moving much faster than would be expected, given the amount of visible matter, stars, gas, and dust that existed in the cluster. According to the laws of Newtonian physics, the galaxies should have been moving much more slowly, and the cluster should have been in danger of flying apart. However, they were staying together. Zwicky hypothesized that there must be some unseen matter exerting additional gravitational pull that was keeping the galaxies in place. This idea was controversial at the time, as the existence of invisible matter was unheard of. But Zwicky's hypothesis sparked further investigation into the nature of gravity and the unseen components of the universe. In the 1970s, astronomer Vera Rubin made similar observations about the rotation curves of galaxies. As she studied the speed at which stars were orbiting the centers of galaxies, Rubin found that the stars in the outer regions of galaxies were moving much faster than expected, given the amount of visible matter in the galaxies. Again, this suggested that there was something unseen, exerting gravitational influence on the stars. This discovery was pivotal in establishing the existence of dark matter. Despite these observational clues, dark matter does not interact with light or other electromagnetic radiation, making it impossible to detect with telescopes. It also does not seem to interact strongly with normal matter, which further complicates its study. If dark matter doesn't emit, absorb, or reflect light, how do we know it's there? The answer lies in its gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the universe. Dark matter is thought to make up most of the mass in galaxy clusters and to play a crucial role in the formation and behavior of galaxies. Without dark matter, galaxies would not have enough mass to hold themselves together, and the gravitational forces required for galaxy formation would not exist. In essence, dark matter is the glue that holds galaxies and galaxy clusters together. The search for dark matter, WIMPs, and other candidates. So what exactly is dark matter made of? Despite its significant presence in the universe, scientists still do not know what dark matter is. One of the leading candidates for dark matter is a class of hypothetical particles called WIMPs, weakly interacting massive particles. WIMPs are thought to have mass but interact only weakly with other matter, which is why they are so difficult to detect. WIMPs are a natural consequence of supersymmetry, a theoretical framework in physics that proposes that for every known particle, there is a corresponding superpartner particle with different properties. In supersymmetry, WIMPs are considered the most likely candidates for dark matter, as they would be able to interact weakly with other particles, but would not emit, absorb, or reflect light. Despite extensive research, no experiment has yet detected WIMPs directly. Several experiments are ongoing to try to detect dark matter particles, including underground detectors that aim to capture the faint interactions between dark matter particles and ordinary matter. The Large Hadron Collider, LHC, is also being used to search for dark matter particles by recreating the conditions just after the Big Bang, where dark matter may have formed. Although no direct evidence of WIMPs has been found so far, the search continues, and scientists are refining their methods to capture dark matter's elusive signature. Other candidates for dark matter include axions, sterile neutrinos, and primordial black holes. But WIMPs remain the most widely studied and discussed. Whatever the true nature of dark matter, its discovery will have profound implications for our understanding of the universe. What is dark energy? While dark matter is responsible for the structure of the universe, dark energy is responsible for its expansion. Dark energy makes up about 68% of the total energy content of the universe and is thought to be driving the accelerated expansion of the cosmos. However, like dark matter, dark energy cannot be observed directly. Instead, its presence is inferred from its effects on the large-scale structure of the universe. The discovery of dark energy came about in the late 1990s, when two independent teams of astronomers were studying the light emitted by distant supernovae. These teams, led by Saul Perlmutter, Adam Rees, and Brian Schmidt, were trying to measure the rate at which the universe was expanding. According to earlier models, the expansion of the universe should be slowing down due to the gravitational pull of matter. However, what the teams discovered was unexpected. The expansion of the universe was accelerating, not slowing down. This was a complete surprise, as it was believed that gravity should be slowing the universe's expansion over time. To explain this, scientists proposed the existence of dark energy, a mysterious force that counteracts gravity and pushes the universe apart. Dark energy is thought to have been responsible for the acceleration of the universe's expansion, particularly in the last 5 billion years. Unlike dark matter, which has a gravitational pull and draws matter together, dark energy appears to have a repulsive effect, pushing galaxies farther apart. Dark energy is thought to be a form of vacuum energy, which is the energy that fills empty space. According to quantum field theory, even empty space is filled with a fluctuating energy field, and dark energy may be a manifestation of this field. Alternatively, dark energy could be a property of space-time itself, an intrinsic force that exists throughout the universe. The role of dark matter and dark energy in the fate of the universe. Dark matter and dark energy play fundamental roles in shaping the fate of the universe. While dark matter acts as the gravitational glue that holds galaxies, galaxy clusters, and other large-scale structures together, dark energy is causing the universe to expand at an increasing rate. The balance between these two forces will ultimately determine the fate of the universe. If dark energy continues to accelerate the expansion of the universe, it could lead to a big freeze scenario, where galaxies move farther and farther apart, stars burn out, and the universe becomes increasingly cold and empty. This scenario is the most widely accepted theory for the ultimate fate of the universe, given the current evidence for the accelerated expansion of the cosmos. Alternatively, if dark matter and gravity ultimately overcome the effects of dark energy, the universe could eventually slow its expansion and collapse in on itself, leading to a big crunch. However, this scenario seems unlikely given the current observations that suggest dark energy is driving an ever-accelerating expansion. There's also a possibility that dark energy could cause the expansion of the universe to accelerate so rapidly that it rips apart galaxies, stars, and even atoms, a scenario known as the Big Rip. While the specifics of dark energy's behavior remain uncertain, it is clear that it will play a decisive role in the ultimate fate of the universe. The ongoing search for dark matter and dark energy. While dark matter and dark energy remain some of the greatest mysteries in modern physics, researchers around the world are working tirelessly to uncover their true nature. New experiments and observational tools, such as the James Webb Space Telescope and next-generation particle accelerators, will continue to probe the depths of the universe, searching for signs of dark matter and dark energy. As we advance our understanding of these invisible forces, we may one day uncover their origins, their roles in the cosmos, and how they relate to the fundamental nature of space, time, and gravity. Dark matter and dark energy may hold the key to understanding the very structure of the universe, from the smallest particles to the largest galaxies, and may ultimately lead to a unified theory of everything that links together all the forces of nature. Conclusion: dark matter and dark energy, the invisible forces shaping the cosmos. Dark matter and dark energy are two of the most profound and mysterious components of the universe. Despite their invisibility, their influence on the cosmos is undeniable. Dark matter acts as the gravitational force that binds galaxies and galaxy clusters together, while dark energy drives the accelerated expansion of the universe. The search for dark matter and dark energy is at the forefront of modern cosmology, with scientists developing new theories, experiments, and technologies to probe these hidden forces. While we have made significant progress in understanding their effects, the true nature of these invisible forces remains a tantalizing mystery. As we continue to explore the universe, the discovery of dark matter and dark energy will likely provide some of the most important insights into the nature of reality, the structure of the cosmos, and the ultimate fate of the universe itself. When we think of the universe and its forces, we often picture vast cosmic phenomena such as galaxies, black holes, and supernovae, large-scale events that shape the fabric of reality. However, there are forces that operate at a much more intimate level, affecting everything from the behavior of atoms to the way light travels through space. These forces are the electromagnetic forces, invisible yet immensely powerful interactions that govern the behavior of charged particles and energy fields. From the light we see to the electric currents powering our devices, electromagnetic forces are the reason for so much of the behavior we take for granted in our daily lives. The study of electromagnetism, one of the four fundamental forces of nature, has led to revolutionary discoveries, including electricity, magnetism, and the very nature of light itself. But despite our everyday interaction with these forces, we may not fully understand their complexity or the deep hidden role they play in shaping the universe. In this chapter, we will explore the invisible world of the electromagnetic force, how it works, the particles involved, and how it shapes everything from the smallest atoms to the largest cosmic structures. we will uncover how electromagnetism is central to both our existence and the functioning of the universe at large, as well as the potential for harnessing its power to unlock the mysteries of space. What is the electromagnetic force? The electromagnetic force is one of the four fundamental forces of nature, alongside gravity, the weak nuclear force, and the strong nuclear force. The electromagnetic force is responsible for the interaction between charged particles, such as electrons and protons, and is the force that governs the behavior of electricity and magnetism. It is one of the most pervasive forces in the universe, influencing everything from the behavior of light to the interactions between matter and energy. Electromagnetism is unique among the fundamental forces because it operates both at a distance and in direct contact. It can act across vast distances, such as the force that attracts the Earth's magnetism or causes solar radiation to travel through space, or on the smallest scales, such as the way electrons interact within atoms. It also manifests in two primary forms: electric forces and magnetic forces. Electric force. The electric force arises from the interaction of electric charges. Positive charges repel other positive charges, while negative charges repel other negative charges. However, positive and negative charges attract each other. This attraction and repulsion form the basis for how electric fields operate in the universe. The electric field is a region around a charged particle where the electric force can be felt. For example, when you rub a balloon on your hair, you are transferring electric charge to the balloon, giving it a negative charge. As a result, the balloon will attract your hair because opposite charges attract. This phenomenon can be explained through the electric field and the interaction between charged particles. Electricity, as we know it, is the flow of electric charge through a material, typically a conductor like copper. Electric currents are created when electrons move through a conductor, driven by the presence of an electric field. The potential energy that drives this movement is the basis for electrical power and all the technologies that rely on it, from the lights in our homes to the devices we use daily. Magnetic force. The magnetic force arises from the movement of electric charges. When charged particles move, they create a magnetic field, and this magnetic field can exert forces on other moving charges. This is the foundation of how magnets work and why electricity and magnetism are so closely related. A magnetic field is a vector field that exerts a force on moving charges or magnetic materials. Just like an electric charge, a magnetic pole can either attract or repel another magnetic pole. However, unlike electric charges, magnetic poles always come in pairs, a north pole and a south pole. If you break a magnet in half, you end up with two smaller magnets, each with its own north and south pole. The relationship between electricity and magnetism was first explored systematically in the 19th century by physicist Hans Christian Ørsted, who discovered that a current-carrying wire produces a magnetic field around it. This discovery led to the field of electromagnetism, the study of the interconnected nature of electric and magnetic fields. James Clerk Maxwell, in the mid-1800s, later formulated a set of equations, now known as Maxwell's equations, that describe the fundamental laws of electromagnetism and unify electric and magnetic forces into one coherent theory. Magnetic fields are responsible for the behavior of electric motors, generators, and countless other devices that harness electromagnetic forces. Additionally, the Earth's own magnetic field, generated by the movement of molten iron within its core, shields our planet from the harmful effects of solar radiation, including charged particles from the sun that could otherwise strip away our atmosphere. The speed of light and electromagnetic waves. One of the most important aspects of the electromagnetic force is its ability to transmit energy in the form of electromagnetic waves. These waves consist of oscillating electric and magnetic fields that propagate through space at the speed of light. These waves are the carriers of light and all other forms of electromagnetic radiation, including radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. The speed of light in a vacuum is a fundamental constant of nature, denoted as c, and equal to approximately 299,792,458 meters per second. This speed is the upper limit for how fast information or energy can travel through space, according to special relativity. Electromagnetic waves, such as visible light, travel at this speed and are the means by which we observe the universe. The electromagnetic spectrum spans a broad range of frequencies, with visible light occupying only a small fraction of that range. Each type of electromagnetic radiation has different properties based on its wavelength and frequency. Radio waves, for example, have much longer wavelengths and lower frequencies than visible light, while X-rays and gamma rays have much shorter wavelengths and higher frequencies. These electromagnetic waves play a crucial role in our daily lives. They are responsible for telecommunication, radio and television broadcasts, and the Internet, which rely on radio waves and microwaves to transmit information. The study of the electromagnetic spectrum has also been vital for our understanding of the universe, allowing astronomers to detect and study everything from distant stars and galaxies to black holes and quasars. Electromagnetic fields and their role in the universe. Electromagnetic forces are not just limited to small-scale interactions like those between electrons and protons. They also play a crucial role in large-scale cosmic phenomena. One of the most significant roles of electromagnetic fields in the universe is in the formation and behavior of stars, nebulae, and galaxies. Plasma, the fourth state of matter, is composed of charged particles and is highly affected by electromagnetic forces. Stars are essentially giant balls of plasma where the nuclear fusion process generates energy through the interaction of charged particles. Magnetic fields within stars can influence their behavior, leading to phenomena like solar flares and coronal mass ejections, powerful bursts of energy and particles that can affect space weather and impact Earth's magnetic field. The interstellar medium, the matter and radiation that exists between stars in a galaxy, is also largely composed of plasma and is shaped by electromagnetic forces. Magnetic fields within the galaxy help guide the movement of gas and dust, influencing the formation of stars and planetary systems. One of the most exciting areas of research in astrophysics is the study of magnetars, a type of neutron star with extremely strong magnetic fields. The magnetic fields of magnetars are trillions of times stronger than Earth's magnetic field, and these stars emit intense bursts of radiation and X-rays. The study of these exotic objects has provided important insights into the role of electromagnetic forces in the extreme conditions of the universe. The relationship between electromagnetism and other fundamental forces. Electromagnetic forces, while incredibly powerful, are only one part of the story when it comes to the forces that govern the universe. The other three fundamental forces of nature, gravity, the strong nuclear force, and the weak nuclear force, also play important roles in shaping reality. In particular, the strong nuclear force and the weak nuclear force are responsible for the behavior of atomic nuclei. The strong force binds protons and neutrons together in the nucleus of an atom, while the weak force is responsible for processes like radioactive decay and nuclear reactions that power stars. Both of these forces are short-range forces, acting only at the level of atomic particles and are much stronger than gravity, but they are still ultimately part of the standard model of particle physics. One of the greatest challenges of modern physics is unifying these forces into a single theory of everything that can explain how they all work together. While electromagnetism has been successfully described by Maxwell's equations and quantum electrodynamics, and the strong and weak forces are described by the Standard Model, gravity remains the outlier. Scientists are still searching for a unified theory that can incorporate gravity, electromagnetism, and the nuclear forces into one comprehensive framework, such as string theory or loop quantum gravity. Electromagnetism in modern technology. Electromagnetic forces are the foundation of much of the technology we use today. Electricity, in particular, is the driving force behind much of modern civilization, powering our homes, industries, and digital devices. The development of technologies such as the electric motor, generators, and transformers has allowed us to harness electromagnetic forces to perform useful work, transforming the way we live. In addition to electricity, magnetism plays a crucial role in many modern technologies. Magnetic resonance imaging, MRI, for example, is a medical imaging technique that relies on the principles of electromagnetism to produce detailed images of the inside of the human body. Hard drives, used for storing digital information, also rely on magnetic fields to write and read data. Furthermore, electromagnetic waves are the basis of modern communication technologies, including radio, television, cell phones, and the internet. The ability to transmit data using electromagnetic waves has revolutionized the way we communicate and interact with the world. The future of electromagnetic theory and space exploration. As we look to the future, the study of electromagnetism will continue to play a crucial role in space exploration and our understanding of the universe. Electromagnetic forces are central to the design of space probes, telescopes, and other instruments used to explore the cosmos. In particular, the study of electromagnetic radiation across the entire spectrum, from radio waves to gamma rays, will provide key insights into the origin and evolution of the universe. One exciting area of research is the use of electromagnetic propulsion systems for deep space travel. Technologies such as ion drives and magnetoplasma dynamic propulsion use electromagnetic forces to propel spacecraft at high speeds, offering the possibility of faster and more efficient space exploration. The continued study of electromagnetism, combined with advances in quantum mechanics and astrophysics, promises to reveal even more about the nature of the universe, from the smallest particles to the largest cosmic structures. Conclusion: electromagnetic forces, the invisible energy that powers the universe. The electromagnetic force is one of the most powerful and pervasive forces in the universe. From the smallest atoms to the largest galaxies, electromagnetism governs the interactions between charged particles and the behavior of light and energy. It plays a fundamental role in the structure of matter, the dynamics of the cosmos, and the technologies that shape our modern world. While we have a deep understanding of electromagnetism in many ways, much about its true nature remains a mystery. The connection between electromagnetism and the other fundamental forces of nature, the possibility of unifying these forces into a single theory, and the potential for further harnessing electromagnetic forces for technological advancement all present exciting frontiers in physics and engineering. As we continue to explore the universe, the electromagnetic force will undoubtedly remain a central part of our understanding of the cosmos and our place within it. From the smallest quantum particles to the vast expanse of space, electromagnetism is the invisible force that powers the universe. When we look up at the night sky, we are often awestruck by the sheer vastness of the universe. From the twinkling stars to the distant galaxies, we marvel at the majestic celestial objects that seem to move with perfect order. Behind this cosmic dance is a force that governs everything from the smallest particle to the largest galaxy: gravity. While we experience the effects of gravity every day, from the weight of our bodies to the pull of objects toward the Earth, gravity remains one of the most mysterious and powerful forces in the universe. Gravity is the force that keeps the planets in orbit around the Sun, that binds stars and galaxies together, and that even affects the passage of time itself. Yet, despite its immense power and its central role in shaping the structure of the universe, gravity has eluded a complete explanation. It is the only fundamental force that remains unexplained by the standard model of particle physics, and its true nature continues to challenge scientists. In this chapter, we will explore the concept of gravity, its effects on the cosmos, how it was first understood, and how it continues to puzzle physicists. We will examine the relationship between gravity and the fabric of space-time, and discuss some of the most groundbreaking discoveries in the study of gravity, including black holes, gravitational waves, and the ongoing search for a unified theory of gravity. What is gravity? At its core, gravity is a force of attraction that pulls objects toward each other. The more massive an object, the stronger its gravitational pull. It is the reason that objects fall to the ground when dropped, the reason the Earth orbits the Sun, and the reason we stay firmly planted on the surface of our planet. While gravity is the force that keeps us grounded, it also shapes the structure of the entire universe, from the formation of planets and stars to the behavior of galaxies, and even the expansion of space itself. The concept of gravity has been around for centuries, but the way we understand it has evolved dramatically over time. The first real breakthroughs in understanding gravity came from Isaac Newton in the late 17th century. Newton's law of universal gravitation. In 1687, Isaac Newton published his Principia Mathematica, in which he formulated the law of universal gravitation. Newton's law states that every particle of matter in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. In simpler terms, the force of gravity depends on two factors: how much mass an object has and how far apart the objects are. Newton's law allowed scientists to predict the motion of celestial bodies with great precision. It explained why the planets orbit the sun and why the moon orbits the earth. It also provided a framework for understanding the motion of objects on Earth, from falling apples to the orbits of satellites. Newton's theory of gravity was groundbreaking because it showed that gravity was a universal force that acted across vast distances. It was no longer thought of as just a force between nearby objects. Instead, gravity was the force that held the universe together, keeping the Earth, the moon, and the planets in motion. However, Newton's law was not without its limitations. While it worked brilliantly for most practical purposes, it couldn't explain certain phenomena, particularly those involving extreme conditions, like the behavior of light near massive objects or the orbits of planets around the sun. Einstein's theory of general relativity. In the early 20th century, Albert Einstein revolutionized our understanding of gravity with his theory of general relativity. General relativity, published in 1915, presented a radically different view of gravity, one that went beyond the idea of gravity as a force between masses. Instead of thinking of gravity as a force pulling objects toward each other, Einstein proposed that gravity is the curvature of space-time caused by the presence of mass and energy. In Einstein's view, massive objects like the Earth and the Sun warp the fabric of space and time around them. This curvature creates what we perceive as gravity, and objects move along the curved paths dictated by the geometry of space-time. Imagine a heavy ball placed on a stretched rubber sheet. The ball causes the sheet to curve, and smaller objects roll toward the ball as a result. In this analogy, the ball represents a massive object like the sun, and the rubber sheet represents space-time itself. One of the key insights of general relativity is that space and time are not separate entities, but are instead woven together into a four-dimensional fabric called space-time. This fabric can be warped by mass and energy, and this warping affects the motion of objects. This is why, in general relativity, gravity is not seen as a force acting at a distance, as Newton proposed, but as a geometrical property of space-time itself. Einstein's theory was tested and confirmed in a variety of ways, most famously during the solar eclipse of 1919, when British astronomers observed that the light from stars was bent as it passed near the sun, exactly as Einstein had predicted. This phenomenon, known as gravitational lensing, is one of the many predictions of general relativity that have been confirmed by subsequent observations. General relativity also predicted the existence of black holes, regions of space where gravity is so strong that not even light can escape. These black holes are some of the most fascinating and mysterious objects in the universe, and they provide a powerful demonstration of the influence of gravity on space-time. Black holes, the ultimate test of gravity. One of the most extreme consequences of Einstein's theory of general relativity is the concept of black holes. A black hole is a region of space where gravity is so intense that it warps space-time to the point where not even light can escape. The boundary of a black hole is called the event horizon, and once an object crosses this threshold, it is pulled inexorably toward the center of the black hole, where it is crushed to an infinitely small point in what is known as a singularity. Black holes form when massive stars run out of fuel and collapse under their own gravity, compressing their mass into a singularity. This process creates a gravitational field so strong that anything, including light, that comes too close is drawn in. Black holes were once considered theoretical curiosities, but today there is substantial evidence that they exist, with many astronomers observing their effects on nearby stars and gas clouds. The Event Horizon Telescope, EHT, which captured the first image of a black hole in 2019, provided a groundbreaking image of the black hole at the center of the M87 galaxy. This historic image was one of the most significant confirmations of Einstein's theory of general relativity and its predictions about the behavior of black holes. The study of black holes has deepened our understanding of gravity and its role in shaping the universe. Black holes are not only fascinating objects in their own right, but they also provide valuable insights into the nature of space-time and the limits of our understanding of physics. They may even hold the key to understanding the ultimate fate of the universe and the nature of the Big Bang. Gravitational waves, the ripple in space-time. In 2015, another milestone in our understanding of gravity came with the detection of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects. These waves were predicted by Einstein's general theory of relativity over a century ago, but it wasn't until the advent of extremely sensitive instruments, like the Laser Interferometer Gravitational Wave Observatory, LIGO, that we were able to directly observe them. Gravitational waves are produced by some of the most violent events in the universe, such as the merging of black holes or the collision of neutron stars. When two massive objects like black holes spiral toward each other and merge, they create gravitational waves that travel outward at the speed of light, carrying information about the objects that created them. The detection of gravitational waves opened up an entirely new way of observing the universe. Instead of relying solely on electromagnetic radiation, such as visible light, scientists can now detect gravitational waves, which carry information about the most extreme cosmic events. This breakthrough provides a new tool for exploring the universe, and it could lead to even more exciting discoveries about the nature of gravity and the cosmos. The search for a unified theory of gravity. Despite the monumental success of general relativity, gravity remains the one force that has eluded a complete and unified description. While quantum mechanics has successfully described the behavior of particles at the smallest scales, and the other fundamental forces, the strong nuclear force and the weak nuclear force, have been explained by the standard model of particle physics, gravity remains outside this framework. One of the most significant challenges in modern physics is the search for a theory of quantum gravity, a unified theory that can describe gravity at both the large scales of galaxies and the small scales of quantum particles. The current leading candidates for this theory are string theory and loop quantum gravity, but neither has yet been experimentally verified. The quest for a unified theory of gravity remains one of the most important goals in theoretical physics, and it promises to revolutionize our understanding of space, time, and the forces that shape the universe. Gravity's role in the future of the universe. Gravity is not just the force that shapes the present-day universe, it also plays a central role in determining the future of the cosmos. One of the key questions in cosmology is whether the expansion of the universe will continue indefinitely, or whether gravity will eventually slow it down and cause it to collapse. There are three main scenarios for the ultimate fate of the universe. 1. The Big Freeze. If dark energy continues to accelerate the expansion of the universe, galaxies will drift farther apart, stars will burn out, and the universe will become an ever colder, emptier place. 2. The Big Crunch. If gravity ultimately overcomes dark energy, the universe will slow its expansion and eventually collapse in on itself, leading to a Big Crunch, where everything is compressed into a singularity. 3. The Big Rip. If dark energy increases in strength, it could tear apart galaxies, stars, and even atoms in a scenario known as the Big Rip. In all these scenarios, gravity will be a driving force, either slowing down the expansion, causing a collapse, or potentially playing a role in the destruction of the universe. The search for answers to these questions will continue to shape the study of gravity and cosmology for generations to come. Conclusion. Gravity, the invisible force that holds the cosmos. Together, gravity is the force that governs everything from the motion of the planets to the behavior of light. It is the glue that holds galaxies, stars, and planets together and shapes the structure of the universe. Despite its profound effects on the cosmos, gravity remains one of the most mysterious and complex forces in the universe. From Newton's law of universal gravitation to Einstein's theory of general relativity, our understanding of gravity has evolved over centuries, yet many questions remain unanswered. The discovery of black holes, the detection of gravitational waves, and the ongoing search for a quantum theory of gravity all point to the continued importance of gravity in shaping the future of the universe. As we continue to explore the cosmos and study the fundamental forces of nature, gravity will remain at the center of our quest to understand the universe, from the deepest black holes to the most distant galaxies, and from the small scales of quantum mechanics to the largest scales of cosmology. Gravity is the invisible force that holds the cosmos together, shaping everything we know and everything we have yet to discover. While gravity may govern the motion of planets and galaxies, and electromagnetism shapes the behavior of light and electric currents, two other invisible forces, the strong nuclear force and the weak nuclear force, govern the behavior of the atomic world. These two forces, though operating on completely different scales, are essential for the very existence of matter, and without them, the universe as we know it would not exist. They govern the interaction of particles inside the nucleus of atoms and are central to the processes that power the stars and facilitate nuclear reactions on Earth. In this chapter, we will explore the strong nuclear force and the weak nuclear force, the key role they play in the fabric of matter, and how these forces shape the universe at the most fundamental level. We will also discuss how scientists discovered these forces, how they are described by modern physics, and how they differ in their characteristics and effects. What is the strong nuclear force? The strong nuclear force, often simply called the strong force, is the force that binds protons and neutrons together in the nucleus of an atom. It is the most powerful of the four fundamental forces of nature and is responsible for the stability of matter. Without the strong nuclear force, atomic nuclei, and therefore matter itself, would not exist. The strong force is responsible for holding together the particles that make up atomic nuclei. Protons and neutrons are composed of smaller particles called quarks, which are held together inside these particles by the strong interaction. The force that binds quarks together inside protons and neutrons is called the strong force. It is short-range, meaning it operates only at the scale of atomic nuclei, typically at distances on the order of 1 femtometer, 10 to 15 meters. The strong nuclear force is incredibly powerful but has a very short range. In fact, it is about 100 times stronger than electromagnetism and more than 1,000,000 times stronger than the gravitational force. However, this force only operates over extremely short distances, when quarks are confined within particles like protons and neutrons. As the distance between particles increases, the strong force rapidly decreases, which is why it does not have an effect on larger scales, like the size of an atom. The role of the strong force in atomic nuclei. Inside an atom, protons and neutrons are held together in the nucleus by the nuclear strong force. If it were not for this force, the repulsive electromagnetic force between the positively charged protons would cause them to fly apart. The strong force overcomes this repulsion and binds protons and neutrons together. At the quantum level, the strong force is mediated by gluons, the force carrier particles for the strong interaction. Gluons are exchanged between quarks inside protons and neutrons, binding them together. These gluons do not have mass, but they carry the strong force between quarks. Gluons interact in a way that keeps quarks confined within particles, an effect known as confinement. In addition to holding protons and neutrons together, the strong force also plays a role in the process of nuclear fusion, which powers the stars. In nuclear fusion, atomic nuclei collide and merge, releasing an immense amount of energy. This process relies on the strong force to overcome the electromagnetic repulsion between the positively charged protons in the nuclei. Without the strong force, nuclear reactions such as fusion and fission, processes that power stars and nuclear reactors, would not be possible. The weak nuclear force, the force that powers radioactive decay. While the strong nuclear force is responsible for holding protons and neutrons together, the weak nuclear force is responsible for some of the most fascinating and important processes in the universe, including radioactive decay and nuclear reactions. The weak nuclear force is called weak because it is much weaker than the strong nuclear force. However, it is still stronger than gravity and electromagnetism on the subatomic scale. The weak force is essential for processes like the decay of radioactive elements and nuclear fusion in stars. Unlike the strong force, which acts within the nucleus, the weak force can act on a wide variety of particles, including electrons and neutrinos. One of the most important roles of the weak force is in beta decay, a type of radioactive decay that occurs when a neutron in an unstable atomic nucleus transforms into a proton, releasing an electron, beta particle, and an antineutrino. This process changes the identity of the atom and is the fundamental process behind many types of radioactive materials, including carbon-14, which is used in radiocarbon dating to determine the age of ancient artifacts and fossils. The weak nuclear force is mediated by W and Z bosons, the force carrier particles that enable the weak interaction. Unlike the photon, which carries the electromagnetic force, the W and Z bosons are massive and very short-lived. This is one reason why the weak force is short-range and weak compared to other forces like electromagnetism. The mass of the W and Z bosons also means that the weak force can only operate over extremely short distances, typically on the order of 0.1% of the diameter of a typical atom. While the weak force is important in nuclear processes, it also plays a role in the behavior of neutrinos, elusive particles that rarely interact with matter. Neutrinos are produced in huge quantities in the Sun during supernovae and in nuclear reactors, and they are only affected by the weak force. The study of neutrinos and their interactions with the weak force has opened up new areas of research in particle physics and cosmology. How do the strong and weak nuclear forces compare? The strong and weak nuclear forces differ significantly in terms of their strength, range, and the particles they affect. The strong force is responsible for holding protons and neutrons together in atomic nuclei, while the weak force is responsible for processes like radioactive decay and the interactions of neutrinos. The strong force is the most powerful force in the universe, but it only operates over very short distances. In contrast, the weak force has a much shorter range and is weaker in comparison to the strong force, but it is essential for fundamental processes like the transformation of particles in radioactive decay. Both forces operate at the subatomic level and play crucial roles in the behavior of matter at the smallest scales. While the strong force creates the structure of atomic nuclei, the weak force facilitates transformations within those nuclei, enabling the decay and conversion of particles. The relationship between these forces and their role in the standard model of particle physics is key to understanding the behavior of the fundamental building blocks of nature. The role of the strong and weak forces in the universe. At the cosmic scale, the strong and weak nuclear forces play a fundamental role in the creation of stars and the evolution of the universe. The process of stellar nucleosynthesis, the creation of new elements in the cores of stars, relies on the strong force to hold atomic nuclei together and the weak force to transform neutrons into protons and vice versa. The strong force also powers nuclear fusion, which is the process that fuels stars like our Sun, providing the energy necessary for life on Earth. The death of stars, especially massive stars, also involves the strong and weak forces. When a star exhausts its nuclear fuel, its core collapses and the strong force helps create extremely dense objects like neutron stars and black holes. The weak force also plays a role in the supernova explosions that occur when massive stars die, scattering elements like carbon, oxygen, and iron throughout space. These elements are crucial for the formation of new stars and planetary systems, including our own. On a smaller scale, the nuclear reactions that occur in nuclear reactors here on Earth rely on the strong and weak nuclear forces to generate energy. In a nuclear reactor, the strong force is responsible for the binding of protons and neutrons in atomic nuclei, while the weak force governs the decay of radioactive isotopes. Understanding these forces has led to breakthroughs in energy production and medicine, with the development of nuclear power plants and medical techniques like radiation therapy. The unification of the strong and weak nuclear forces. One of the most important challenges in modern physics is the unification of the four fundamental forces. Currently, the strong nuclear force and weak nuclear force are described by the Standard Model of particle physics, but gravity and electromagnetism remain outside this framework. Scientists are working toward a theory that can unify all four forces, a theory of everything. And there are promising candidates, including string theory and grand unified theories, GUTS. In particular, the strong and weak nuclear forces are both part of a broader family of forces called the weak force group. The unification of the weak force and the electromagnetic force into a single framework, known as the electroweak theory, was one of the great successes of modern physics. The work of Sheldon Glashow, Abdus Salam, and Steven Weinberg in the 1970s led to the development of this theory, for which they won the Nobel Prize in 1979. However, the strong force remains a separate force, not yet unified with the weak force or electromagnetism. The quest to unify all the forces into a single framework remains one of the most important goals in theoretical physics, with the hope that a theory of everything could explain the fundamental nature of reality and the forces that govern the universe. Conclusion: the strong and weak forces, the hidden forces of the atomic world. The strong and weak nuclear forces are the invisible forces that govern the behavior of particles at the atomic level. The strong force holds atomic nuclei together, while the weak force governs the transformation of particles in processes like radioactive decay. These forces are essential for the existence of matter and the processes that power stars, drive nuclear reactions, and sustain life on Earth. Though these forces operate on incredibly small scales, their effects are felt across the universe. The strong and weak forces are responsible for the structure and evolution of stars, the creation of new elements, and the behavior of particles in particle accelerators and nuclear reactors. They are the fundamental forces that power the atomic world. As scientists continue to explore the universe, the search for a unified theory that can describe all four fundamental forces remains one of the greatest challenges in physics. But even without a complete understanding of these forces, we can appreciate their immense power and importance. The strong and weak nuclear forces shape the building blocks of matter and drive the processes that govern the cosmos, forces that are invisible but vital to the existence of everything around us. When we look at the universe as a whole, we see a vast interconnected system that is governed by fundamental forces. These forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, shape everything from the smallest subatomic particles to the largest structures in the cosmos. They dictate how matter interacts, how galaxies form, how stars are born and die, and how time and space themselves behave. But there is something deeply fascinating about these forces. While they govern everything we see, they are largely invisible, operating on scales far beyond the reach of our direct observation. These forces exist at the heart of all matter and energy in the universe, shaping the very fabric of reality. Yet, for all that we know about them, we are only scratching the surface of their full potential. In this chapter, we will examine how these fundamental forces shape the cosmos, from the formation of galaxies to the behavior of elementary particles. We'll explore how the forces interact with each other, how they give rise to the universe's structure, and how scientists are striving to unify them into a single, all-encompassing theory. We'll also look at the big picture, considering how these forces govern everything from the smallest atom to the largest galaxy, and how they continue to shape the evolution of the universe. Gravity, the force that binds the cosmos. The first force that governs the large-scale structure of the universe is gravity. Gravity is the force that governs the motion of planets, stars, and galaxies, and it is responsible for the very structure of the universe. Without gravity, stars and galaxies would not form, and matter would be scattered across an empty, chaotic void. Gravity works by attracting objects with mass towards each other. It is a long-range force, meaning it can act over vast distances. This is why planets can orbit stars and why moons can orbit planets. Gravity is also the force that causes objects to fall to the ground when dropped, and why we feel our own weight pressing down on us as we stand on Earth. The most famous theory of gravity is Newton's law of universal gravitation, which describes gravity as a force that acts between two objects with mass. However, this view was later expanded by Albert Einstein's theory of general relativity, which showed that gravity is not simply a force, but a curvature of space-time caused by the presence of mass. According to general relativity, massive objects like stars and planets bend the fabric of space-time around them, and this bending is what causes the gravitational attraction we feel. While gravity is the weakest of the four fundamental forces, its effects are felt across the universe. It governs the motion of galaxies, controls the orbits of planets, and is responsible for the creation of black holes, regions of space where gravity is so intense that not even light can escape. Gravity is what holds the universe together, and it is one of the most essential forces in the cosmos. Electromagnetic forces, the invisible force behind light and energy. The second fundamental force, electromagnetism, plays a key role in shaping the universe on both the macroscopic and microscopic levels. Electromagnetism governs the behavior of charged particles, such as electrons and protons, and is responsible for phenomena like light, electricity, and magnetism. The electromagnetic force has two main components: electric forces and magnetic forces. Electric forces act between particles with electric charge, while magnetic forces act between moving charges. These two forces are interconnected and are described by Maxwell's equations, which unify the study of electric and magnetic fields into a single theory. At the atomic level, the electromagnetic force governs the interactions between electrons and atomic nuclei, holding atoms and molecules together. It is also the force that governs the behavior of light and other forms of electromagnetic radiation, such as radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. These forms of radiation are all part of the electromagnetic spectrum, and they are essential for communication, power generation, and many other aspects of modern life. On a larger scale, the electromagnetic force is responsible for magnetism and the formation of magnetic fields, which are essential in the functioning of devices like electric motors and transformers. The Earth's magnetic field also protects us from harmful solar radiation, deflecting charged particles away from our planet. The electromagnetic force is incredibly powerful compared to gravity. While gravity governs the motion of massive objects like planets, electromagnetism operates at the level of individual particles. This is why electricity can be so powerful, and why magnetic fields can influence the motion of particles and even bend light. However, unlike gravity, the electromagnetic force can be both attractive and repulsive, depending on the charge of the particles involved. The strong nuclear force, the glue of atomic nuclei. The strong nuclear force is the most powerful force in the universe, but it only acts over extremely short distances. This force binds protons and neutrons together inside atomic nuclei, holding them together against the electromagnetic repulsion between positively charged protons. Without the strong force, atomic nuclei would fly apart due to the repulsion between protons. The strong force operates between quarks, the fundamental particles that make up protons and neutrons. Quarks are held together by gluons, the force carrier particles for the strong interaction. The strong force is incredibly strong but has a very short range, about the size of an atomic nucleus. This is why it has such an important role in the stability of matter, but it does not have the same influence on larger scales. The strong force is also responsible for nuclear fusion, the process that powers stars. In stars, hydrogen nuclei fuse to form helium, releasing vast amounts of energy. The strong force is what allows these nuclear reactions to occur, overcoming the repulsive electromagnetic force between positively charged nuclei. The weak nuclear force, the force of particle decay. The weak nuclear force is responsible for processes like radioactive decay and nuclear reactions. While it is much weaker than the strong nuclear force, it plays a crucial role in the transformation of particles. The weak force is responsible for processes like beta decay, where a neutron is transformed into a proton, releasing an electron and a neutrino. The weak force is mediated by massive particles called ALO and Z bosons. Unlike the photon, which mediates the electromagnetic force, and the gluon, which mediates the strong force, the W and Z bosons are very heavy, which is why the weak force is short range and weak compared to other forces. The weak force is essential for nuclear reactions, including those that power the sun and other stars. The four fundamental forces and their interactions. The four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, each operate in different ways, but they are all interconnected. For example, the strong force and the weak force both operate within atomic nuclei, determining the behavior of particles at the most fundamental level. Electromagnetism governs the behavior of particles on larger scales, while gravity governs the motion of objects in space. One of the greatest challenges in modern physics is to unify these four forces into a single theory that can explain all interactions at every scale. While we have a good understanding of how gravity and electromagnetism work, the strong and weak forces remain the subject of intense study. The standard model of particle physics successfully describes the electromagnetic, weak, and strong forces, but it does not include gravity. The search for a theory that can unite these forces is one of the most important quests in physics today. How these forces shape the universe. The interplay between the strong, weak electromagnetic and gravitational forces shapes the entire universe. These forces are responsible for the formation of stars, galaxies, and planets, and they govern the behavior of matter from the smallest subatomic particles to the largest cosmic structures. In the early universe, just moments after the Big Bang, the forces of nature were likely unified, meaning they all existed as one force. As the universe cooled and expanded, these forces began to separate and behave differently, giving rise to the distinct fundamental forces we observe today. The strong and weak forces shaped the creation of the first atomic nuclei, while gravity and electromagnetism played a role in the formation of galaxies and stars. On the cosmic scale, gravity shapes the structure of the universe, pulling matter together to form galaxies, stars, and clusters of galaxies. Electromagnetism governs the formation of stars, planets, and the behavior of light. The strong and weak nuclear forces are responsible for the nuclear processes that power stars and generate the elements needed for life. These forces also govern the evolution of the universe. For instance, gravity has caused the universe to expand and form large structures, while the electromagnetic force has enabled the creation of complex molecules and the emergence of life. The strong and weak forces continue to shape the behavior of matter, from the decay of radioactive elements to the formation of new stars and galaxies. The unification of forces and the search for a theory of everything. One of the most exciting areas of research in modern physics is the quest for a theory of everything, TOE, a unified theory that can describe all four fundamental forces in a single framework. Currently, gravity is described by general relativity, while the other three forces are explained by the standard model of particle physics. However, these two theories do not yet fit together, and scientists are searching for a way to unify them. The leading candidates for a theory of everything include string theory and loop quantum gravity. String theory proposes that the fundamental particles of the universe are not point-like objects, but tiny, vibrating strings. These strings can vibrate at different frequencies, and their interactions create the forces we observe. Loop quantum gravity, on the other hand, attempts to describe gravity in a quantum framework, suggesting that space-time itself is quantized, like matter. Despite the exciting progress in theoretical physics, a complete theory of everything remains elusive. The unification of these forces would not only revolutionize our understanding of the universe, but also provide the keys to unlocking the most fundamental mysteries of reality, from the nature of space-time to the origins of the universe itself. Conclusion: the forces that shape our universe. The four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are the invisible forces that govern everything from the smallest particles to the largest galaxies. Together, these forces shape the structure of the universe, determine the behavior of matter, and hold the key to understanding the nature of reality. While we have made incredible progress in understanding these forces, much remains to be discovered. The quest to unify these forces into a single theory of everything continues to drive the field of physics forward. As we continue to explore the universe, the fundamental forces will remain at the heart of our efforts to understand the cosmos, and they will continue to reveal the deepest mysteries of the universe. Imagine being able to travel across vast distances of space and time in the blink of an eye. What if we could journey between galaxies, or even between different universes, bypassing the limitations of our current technology and the speed of light? It sounds like science fiction, but one of the most intriguing concepts in theoretical physics is that wormholes might make such interdimensional travel possible. Wormholes, also known as Einstein-Rosen bridges, are theoretical passages through space-time that could connect distant points in the universe. These shortcuts through space and time could potentially allow us to travel vast distances instantaneously. But could wormholes really exist? Could they be used for time travel? And, if they do exist, how would we traverse them to explore other dimensions, alternate realities, or even parallel universes? In this chapter, we will explore the nature of wormholes, how they could be linked to time travel and parallel universes, and the scientific theories that suggest they might be more than just a figment of our imagination. We will dive into the mathematical foundations of wormholes, their possible connections to other forces in the universe, and the groundbreaking implications they have for the future of space exploration and our understanding of the universe. What is a wormhole? A wormhole is a hypothetical structure in space-time that acts as a shortcut between two distant points in the universe. The concept of a wormhole arises from the theory of general relativity, which describes the gravitational interaction between matter and the fabric of space-time. In Einstein's theory, space and time are not separate entities, but are woven together into a four-dimensional continuum known as space-time. Massive objects such as stars and planets warp space-time around them, and this curvature is what we perceive as gravity. A wormhole is essentially a tunnel through this space-time fabric. Picture it like a tunnel with two ends, one at a point in space-time and the other at a distant point. The idea is that instead of traveling through the vast expanse of space, you could theoretically enter a wormhole and emerge instantaneously at the other end, bypassing the normal constraints of space and time. Wormholes are often referred to as Einstein-Rosen bridges, after the physicists Albert Einstein and Nathan Rosen, who first proposed the idea in 1935. They showed that the equations of general relativity allow for the existence of a bridge between 2 points in space-time. This bridge would be like a tunnel with a highly curved space-time geometry, potentially allowing for faster-than-light travel across vast distances. While the concept of a wormhole is theoretically sound, we have no empirical evidence to suggest that they exist in reality. Types of wormholes: traversable and non-traversable. Not all wormholes are created equal, and their potential for use as interdimensional travel gateways depends on their structure. There are two main types of wormholes in theoretical physics. 1. Non-traversable wormholes. These are the kind of wormholes that might exist in nature, but they are not usable for travel. These wormholes would collapse too quickly for anything or anyone to pass through them. Essentially, they would act as tunnels that only exist temporarily and are unstable, meaning they cannot sustain the passage of matter. In such a case, the entry and exit points of the wormhole would close before anything could travel through. 2. Traversable wormholes. These are the ideal wormholes for time travel and space exploration. Traversable wormholes are stable enough to allow matter to pass through without causing the tunnel to collapse. In theory, a spaceship could enter one mouth of a traversable wormhole and emerge from the other mouth, in a distant part of the universe. These wormholes would require some form of exotic matter to keep them open, but they could, in theory, provide shortcuts through space-time. While non-traversable wormholes are a possibility, it is the traversable wormholes that excite physicists and offer tantalizing prospects for space travel. However, creating or finding a stable traversable wormhole would require an understanding of exotic matter and energy and technology that far exceeds anything we have today. The connection between wormholes and time travel. One of the most exciting and speculative aspects of wormholes is their potential use in time travel. According to the theory of general relativity, time and space are interconnected and form a four-dimensional fabric known as space-time. Wormholes, which connect 2 points in space-time, could potentially also allow for the manipulation of time. The idea of time travel through wormholes is based on the concept of time dilation. Time dilation occurs when an object moves at very high speeds, close to the speed of light, or is located in a strong gravitational field. Under these conditions, time passes more slowly for the object in motion or near the massive object, compared to an observer at rest or in a weaker gravitational field. This is a direct consequence of general relativity. If wormholes could be used to manipulate time, they might allow for time travel to the past or future. Theoretically, a person traveling through a wormhole could enter the tunnel at one point in time and emerge at another, possibly in the past or future. However, there are many unresolved issues and paradoxes that arise when discussing time travel. One of the most famous paradoxes is the grandfather paradox. The paradox suggests that if you were to travel back in time and change something in the past, such as preventing your grandfather from meeting your grandmother, you could potentially prevent your own birth. This would create a contradiction, as you would not exist to travel back in time and make the change in the first place. Physicists have proposed several potential solutions to these paradoxes, including the idea of multiple timelines or parallel universes. According to some theories, any change made in the past would create a new timeline, one that diverges from the original. This would mean that time travelers might not interfere with their own history, but instead create a new parallel universe. Exotic matter and the stability of wormholes. For a wormhole to remain stable and traversable, it would require a form of matter that is completely different from anything we encounter in our everyday lives. This matter is referred to as exotic matter, and it is theorized to have negative energy density. In essence, exotic matter would have the opposite effect of ordinary matter. Instead of pulling objects together, like gravity does, it would push objects apart. Exotic matter is necessary to keep a wormhole open because it would counteract the natural gravitational forces that would cause the wormhole to collapse. Without exotic matter, any attempt to travel through a wormhole would result in the tunnel collapsing before the traveler could reach the other end. The concept of exotic matter is rooted in the idea of negative energy, which has been studied in various theoretical frameworks. Casimir energy, a phenomenon that occurs when two conductive plates are placed in a vacuum, is one example of negative energy. However, we have no practical way of creating exotic matter, and it remains purely theoretical at this point. Even if exotic matter exists, we would need to figure out how to manipulate it to create stable, traversable wormholes. This remains one of the biggest challenges in the study of wormholes and time travel. Without the ability to generate exotic matter, wormholes would remain theoretical constructs, and the possibility of time travel or interdimensional exploration would be out of reach. Wormholes and the multiverse. One of the most exciting possibilities that wormholes present is the idea of the multiverse, the notion that there are multiple parallel universes that coexist alongside our own. Some versions of the multiverse theory propose that there are infinite universes, each with its own version of space-time, physical laws, and even different versions of ourselves. Wormholes could theoretically provide a gateway to these parallel universes. If wormholes can connect different points in space-time, then it is possible that they could also connect different universes. In this scenario, a wormhole would not only allow you to travel through space, but through alternate realities or different versions of the universe itself. This idea brings us to the speculative and fascinating concept of multiverse travel. If wormholes could link multiple universes, then traveling through them could allow us to explore different realities. Each universe could have its own set of physical constants, laws of physics, and even histories. For example, one universe might have a version of Earth where a different historical event occurred, leading to an alternate timeline. Another universe might have entirely different physical laws, where the concept of gravity behaves differently, or where life has evolved in ways we can't even imagine. The concept of traveling through wormholes to different universes is still speculative, but it provides a tantalizing glimpse into the potential of wormholes as gateways not just to distant parts of space, but to entirely different realms of reality. Challenges to using wormholes for travel. While the idea of using wormholes for time travel and interdimensional exploration is incredibly exciting, there are significant challenges to making this a reality. For one, the energy required to create or stabilize a wormhole is beyond our current technological capabilities. We would need to generate enormous amounts of energy, likely far more than is currently possible, to manipulate space-time in the way required to create a stable wormhole. Additionally, wormholes, if they exist, may be located in regions of space that are incredibly difficult to reach. They may be near massive objects like black holes, which would make traveling to them extremely dangerous. Even if we could theoretically create a wormhole, the challenges of navigating through it safely would be immense. The concept of time travel paradoxes and the many worlds interpretation of quantum mechanics also raise philosophical questions about the consequences of altering the past or traveling to other universes. If wormholes allow for the creation of new timelines or parallel realities, how would this affect our understanding of free will and causality? Could we change history, or would we merely create new versions of it? Conclusion. The promise and peril of wormholes. Wormholes are one of the most intriguing and speculative concepts in modern physics. They offer the possibility of instantaneous travel across vast distances, time travel to the past or future, and even exploration of parallel universes. While wormholes are still purely theoretical and face many obstacles, including the need for exotic matter and the uncertainty of their existence, they represent a tantalizing possibility for the future of space travel and interdimensional exploration. Whether wormholes are the key to unlocking new realms of reality or whether they remain purely theoretical constructs, their study continues to push the boundaries of our understanding of the universe. As we explore the potential for wormholes and time travel, we may discover new insights into the nature of space, time, and reality itself, opening up possibilities that challenge our imagination and redefine our place in the cosmos. At the heart of the universe lies a mysterious and often elusive concept, space-time. While we are all familiar with the idea of space, the three-dimensional expanse in which we live, breathe, and move, and the passage of time, we tend to think of them as separate entities. We move through space, and time moves forward 1 second at a time as a steady flow. However, the fabric of the universe is not so simple. Space and time are deeply intertwined in a single unified structure known as space-time. The fabric of space-time is not just a passive backdrop for the events of the universe, it is an active participant in the behavior of the cosmos. Space-time bends, warps, and distorts in response to the presence of mass and energy. It is the very structure of space and time that determines the behavior of everything from the smallest particles to the largest galaxies. In this chapter, we will explore the concept of space-time and its importance in understanding the universe. We will look at how space-time is shaped by the fundamental forces of nature, how it interacts with matter and energy, and how the study of space-time has led to some of the most revolutionary discoveries in modern physics, including general relativity, black holes, and gravitational waves. What is space-time? At its most basic level, space-time is the four-dimensional continuum that combines the three dimensions of space with the fourth dimension of time. Instead of thinking of space and time as separate, space-time unites them into a single framework where the three dimensions of space, length, width, and height, are combined with time to create a unified structure. This idea was first proposed by Hermann Minkowski in 1908, and it was later developed by Albert Einstein as a central component of his theory of special relativity. Space-time is often visualized as a fabric or grid that stretches across the universe, and this fabric can be warped or bent by the presence of mass and energy. Objects with mass, such as stars, planets, and black holes, cause this fabric to bend, creating the curvature of space-time. This curvature is what we experience as gravity. One way to imagine space-time is by using the analogy of a trampoline. If you place a heavy ball in the center of a stretched trampoline, it creates a depression in the surface. Smaller balls placed near the larger ball will roll towards it, not because the larger ball is pulling them directly, but because the fabric of the trampoline is curved, causing the smaller balls to move toward the point of greatest curvature. Similarly, in the universe, objects with mass, such as planets or stars, cause the space-time fabric to curve, and this curvature influences the motion of objects around them. For example, the Earth orbits the Sun, not because the Sun is pulling the Earth with an invisible force, but because the Sun's mass causes a distortion in space-time, and the Earth follows the curved paths defined by that distortion. Einstein's theory of general relativity, how space-time bends. The theory of general relativity, proposed by Albert Einstein in 1915, fundamentally changed our understanding of space, time, and gravity. Before general relativity, gravity was understood as a force between two masses, as described by Isaac Newton's law of universal gravitation. However, Einstein's general theory of relativity presented a revolutionary idea. Gravity is not a force acting at a distance, but the result of the curvature of space-time caused by the presence of mass and energy. According to general relativity, objects with mass, such as planets, stars, or even black holes, cause space-time to bend around them. This bending of space-time creates what we perceive as gravity. Instead of objects being pulled by an invisible force, they move along the curved paths of space-time created by massive objects. The more massive an object, the more it warps the fabric of space-time and the stronger its gravitational influence. In this way, general relativity replaced the classical notion of gravity with the idea of space-time curvature. The theory was tested and confirmed in a variety of ways, including the bending of light by gravity, the precession of Mercury's orbit, and the detection of gravitational waves. Each of these observations confirmed that space-time is not a static backdrop, but a dynamic and active component of the universe that responds to the presence of mass and energy. The role of space-time in the formation of the universe. One of the most fascinating aspects of space-time is its role in the creation and evolution of the universe itself. According to the theory of general relativity, space-time has a beginning, a starting point in time when the universe came into existence. This beginning is marked by the Big Bang, the event that occurred roughly 13.8 billion years ago and led to the formation of the universe. Before the Big Bang, all of the matter and energy in the universe was concentrated in an infinitely small and dense point known as a singularity. At this moment, both space and time themselves began to expand. Space-time itself, as well as the matter and energy that fill it, began to stretch and evolve into the universe we know today. The Big Bang Theory suggests that space-time was created along with the universe and has been expanding ever since. This expansion is still happening today as galaxies move away from each other due to the influence of dark energy. As the universe expands, so too does space-time, carrying the galaxies, stars, and planets along with it. This discovery has profound implications for our understanding of the universe's past and future. In addition to the Big Bang, space-time plays a crucial role in the evolution of cosmic structures such as galaxies, stars, and planets. The interaction between matter and space-time determines how these structures form, how they evolve, and how they interact with each other. Without the curvature of space-time caused by mass and energy, the universe would look very different. Black holes and space-time distortions. One of the most dramatic manifestations of space-time curvature is the black hole, a region of space where gravity is so intense that it warps space-time to the point of creating a singularity. A black hole is formed when a massive star collapses under its own gravity at the end of its life, compressing its mass into an incredibly small point. The event horizon of a black hole is the boundary beyond which nothing, not even light, can escape. Once an object crosses this threshold, it is pulled inexorably toward the singularity at the center of the black hole. The singularity is a point where the curvature of space-time becomes infinite, and the laws of physics as we know them break down. The study of black holes has provided scientists with unique insights into the nature of space-time. For example, time dilation near a black hole is extreme. As you approach the event horizon, time itself appears to slow down relative to an observer far away from the black hole. This phenomenon is a direct result of the intense curvature of space-time near a black hole. Black holes also provide a laboratory for testing the limits of general relativity and quantum mechanics. In particular, the nature of the singularity at the center of black holes remains one of the biggest unsolved mysteries in physics. Understanding the behavior of space-time inside a black hole could hold the key to reconciling the two most successful theories of physics, general relativity and quantum mechanics, gravitational waves, the ripple in space-time. In recent years, scientists have made an exciting discovery that has opened up a new way of observing the universe: gravitational waves. These are ripples in the fabric of space-time caused by the acceleration of massive objects, such as when two black holes merge or when neutron stars collide. Gravitational waves were first predicted by Einstein in 1915 as part of his theory of general relativity. But it wasn't until 2015 that they were directly detected by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves travel at the speed of light and carry information about the objects that created them. Just as light waves can be used to study distant stars and galaxies, gravitational waves offer a new way of probing the universe. They allow us to observe events that are invisible to traditional telescopes, such as the mergers of black holes or the collision of neutron stars. Gravitational waves have opened up a completely new way of studying the cosmos, providing a glimpse into the most extreme phenomena in the universe. The detection of gravitational waves is a major breakthrough in our understanding of space-time. It confirms that space-time is not just a static backdrop, but an active and dynamic entity that can be distorted and warped by the motion of massive objects. Gravitational waves provide us with a new window into the universe, allowing us to study phenomena that were previously beyond our reach. The future of space-time research. The quest for a unified theory. While our understanding of space-time has come a long way since Einstein first formulated his theory of general relativity, many questions remain unanswered. One of the most exciting challenges in modern physics is the search for a unified theory, a theory that can explain both general relativity, which describes gravity on large scales, and quantum mechanics, which governs the behavior of particles at the smallest scales. These two theories are currently incompatible, and scientists are working to develop a quantum theory of gravity that can explain how gravity works at the quantum level. String theory and loop quantum gravity are two leading candidates for such a theory, but neither has been experimentally verified. The search for a unified theory remains one of the most important quests in theoretical physics. In addition, the study of space-time continues to reveal new mysteries about the nature of reality. Could space-time be a more complex and intricate structure than we realize? Are there hidden dimensions or alternate realities that we have yet to discover? Could wormholes or other exotic phenomena provide shortcuts through space-time or even access to parallel universes? The future of space-time research is rich with possibility, and each new discovery brings us closer to understanding the underlying structure of the universe. As we continue to explore the fabric of space-time, we may uncover new insights into the nature of the cosmos, and perhaps even our place within it. Conclusion: the fabric of space-time. Understanding the underlying structure of the universe. Space-time is the framework within which all the forces of nature play out, and it is at the heart of everything we know about the universe. From the Big Bang to black holes, from the expansion of galaxies to the formation of stars, space-time shapes the universe in ways we are only beginning to fully understand. Through the study of space-time, we have gained profound insights into the nature of gravity, time, and the very structure of the cosmos. The discovery of gravitational waves and the ongoing search for a unified theory of gravity promise to reveal even more about the deep hidden nature of space-time. As we continue to probe the universe at ever deeper levels, space-time will remain the central focus of our quest for knowledge. Whether we are studying the birth of stars or searching for answers about the fundamental nature of reality, the fabric of space-time will guide our journey through the cosmos, offering new discoveries, new mysteries, and new possibilities for the future of science and humanity. Time is a concept we experience daily, yet it remains one of the greatest mysteries of the universe. It governs the flow of events, dictates our personal lives, and shapes the evolution of the cosmos. But despite its pervasive presence, time itself is difficult to define and understand. We all have an inherent sense of time, the ticking of the clock, the changing of seasons, the passing of years. But what is time at its core? Is it a fundamental aspect of reality, or is it a construct of the human mind? In this chapter, we will delve into the mysteries of time. We'll explore its philosophical implications, its role in the fabric of the universe, and how it interacts with space-time, the fourth dimension. We will look at the profound implications of time dilation, how general relativity and quantum mechanics approach time, and whether time itself is a physical entity or simply a measurement. Finally, we will explore the arrow of time, the one-way direction of time that we perceive and experience, and whether it is a fundamental feature of the universe or a byproduct of our perception. What is time? Time is often described as the ongoing sequence of events, from the past through the present and into the future. It is a continuous unidirectional flow that we experience as we move through life. But while we can easily describe time in everyday terms, the true nature of time has eluded scientists and philosophers for centuries. What exactly is time? Is it a fundamental aspect of the universe, or is it a human construct, a way for us to make sense of our experience? In physics, time is often treated as a dimension, just like the three spatial dimensions of length, width, and height. Time allows us to locate events within the context of the universe. In the four-dimensional model of spacetime proposed by Albert Einstein, time is inseparable from the three dimensions of space, forming a unified structure. In this framework, space and time are not independent, but rather interwoven into a single continuum. However, this understanding of time as a dimension does not necessarily reveal its true nature. While we can measure time, we cannot observe or touch it. We experience time by perceiving changes, the growth of plants, the movement of the stars, the aging of ourselves and others, but time itself does not seem to have a physical presence. Is it an emergent property of the universe, or is it an aspect of reality that exists independently of the events it measures? The arrow of time. Why does time only move forward? One of the most perplexing aspects of time is its arrow, the fact that time moves in one direction, from past to present to future. This unidirectional flow of time is an inherent feature of our experience, yet it is still not fully understood. Why does time seem to move forward and never backward? Why can't we reverse the flow of time, as we can reverse the direction of a river or a moving object? The concept of the arrow of time is central to our understanding of the nature of time. This arrow is often thought to be driven by entropy, a measure of disorder or randomness in a system. According to the second law of thermodynamics, the total entropy of a closed system tends to increase over time. In simpler terms, this means that systems naturally move from order to disorder, and as they do, time progresses forward. This increasing entropy is what gives time its direction. In a low entropy state, things are organized and time moves in one direction, forward. As entropy increases, systems become more disordered, and this marks the passage of time. The universe as a whole is constantly moving toward greater entropy, which is why we perceive time moving forward. If time were to flow backward, we would observe the reverse of entropy, a universe becoming more ordered, reversing the aging process and undoing the irreversible actions that have already taken place. The arrow of time is particularly significant in our understanding of cosmology and the universe's evolution. If the universe is moving toward a state of maximum entropy, this suggests a future in which all processes are uniform and all energy has been evenly distributed, a scenario often referred to as the heat death of the universe. This increasing entropy is tied to the thermodynamic arrow of time, but it also has deep philosophical and existential implications about the nature of the universe. Time in the context of space-time. One of the most groundbreaking ideas in the study of time comes from Einstein's theory of general relativity. According to general relativity, time is not absolute. It is relative, and its passage can vary depending on speed and gravitational influence. This insight challenges the classical view of time as a constant, unchanging entity, and it opens up new ways of thinking about time's relationship to space. In Einstein's view, space-time is a four-dimensional continuum that includes three spatial dimensions: length, width, height, and one time dimension. The presence of mass and energy warps space-time, causing objects to move along curved paths. This curvature of space-time affects the passage of time. Time dilation is a direct result of this warping. Time passes more slowly for objects that are moving at high speeds or are in strong gravitational fields. This concept has been confirmed in a variety of experiments, including those involving atomic clocks. When atomic clocks are flown in airplanes or placed at high altitudes, they run at slightly different speeds compared to clocks on the ground. This difference is due to the time dilation effects predicted by Einstein's theory. Similarly, clocks placed near large objects with strong gravitational fields, such as Earth or black holes, will also experience time more slowly. The fact that time can be distorted by gravity and velocity means that time is not a universal fixed quantity. It is, instead, a dynamic feature of the universe, intricately linked to the structure of space-time itself. Time, as we experience it, depends on our position in space and our motion relative to other objects. The possibility of time travel. One of the most tantalizing implications of the theory of space-time is the possibility of time travel. If time is not an absolute quantity, but rather something that can be influenced by motion and gravity, could it be possible to travel through time? Could we visit the past or the future, or even alter the course of events? The idea of time travel has long been a staple of science fiction, but general relativity suggests that time travel is not entirely out of the realm of possibility. One of the most famous predictions of Einstein's theory is the existence of closed time-like curves, CTCs, paths through space-time that loop back on themselves. These curves could, in theory, allow an object to travel back in time to an earlier point in the same universe. While CTCs are mathematically valid solutions to the equations of general relativity, there's currently no experimental evidence to suggest they exist. Wormholes, discussed in previous chapters, could also provide a potential pathway for time travel. A wormhole that connects two distant regions of space-time could, in theory, allow for travel to both the past and the future. However, the need for exotic matter to stabilize wormholes, combined with the potential paradoxes of time travel, means that these ideas remain speculative. Despite the fascinating possibilities, time travel faces many obstacles. The most significant of these is the grandfather paradox, the the question of what happens if a time traveler goes back in time and alters events in the past. Would the traveler erase their own existence, or would they create a new timeline? These questions present deep logical and philosophical challenges that physicists and philosophers have yet to resolve. Time and quantum mechanics. While general relativity describes time as a smooth and continuous phenomenon that can be bent and warped by gravity, quantum mechanics offers a different perspective on time. In the quantum realm, particles do not have definite positions or velocities until they are measured. Instead, they exist in a state of superposition, where they can be in multiple states at once. This strange behavior leads to questions about the nature of time itself. In quantum mechanics, time is treated as a parametric variable, a dimension that allows the evolution of quantum states. However, quantum theory does not provide a detailed explanation of how time itself works. Quantum gravity, the attempt to unify general relativity with quantum mechanics, is one of the biggest unsolved problems in physics. Understanding how time behaves at the quantum level could shed light on the nature of time itself. Some physicists have speculated that time, at the smallest scales, may not be continuous. Instead, it could be quantized, existing in discrete steps, like space is thought to be in loop quantum gravity. Others propose that time might emerge from deeper, more fundamental processes, a concept known as emergent time. These theories challenge our everyday understanding of time and suggest that it may not be as fundamental as we believe. Time and the fate of the universe. Time plays a crucial role in the evolution of the universe. According to the Big Bang theory, the universe began as a singularity, a point of infinite density and zero volume, and has been expanding ever since. This expansion is a direct result of the passage of time. Time has been moving forward since the Big Bang, carrying the universe through its various stages, from the formation of the first atoms to the creation of stars and galaxies. The future of time in the universe is still uncertain. If the expansion of the universe continues indefinitely, it could eventually lead to the heat death of the universe, a state in which all energy is evenly spread and the universe becomes cold and dark. Alternatively, the universe could collapse in a big crunch, where gravity overcomes the expansion, causing everything to collapse back into a singularity. Either way, the passage of time will be the guiding force that shapes the ultimate fate of the universe. Conclusion. The mystery of time. Can we ever understand its true nature? Time is one of the most fundamental aspects of our existence, yet it remains one of the most mysterious. While we can measure time and experience its passage, we still do not fully understand what time is or how it works. Time is deeply woven into the fabric of the universe, and its relationship to space, gravity, and quantum mechanics is a central question in modern physics. The study of time has led to profound insights into the nature of the universe, from the Big Bang to the expansion of space, from the theory of general relativity to the strange world of quantum mechanics. As we continue to explore the nature of time, we may uncover new theories that challenge our fundamental understanding of reality, revealing new possibilities for time travel, the origin of the universe, and the future of existence itself. Though time may be an enigma, it is clear that our pursuit of its understanding will continue to be one of the most exciting and transformative areas of scientific inquiry. Whether we can ever truly understand the nature of time, its fundamental mysteries will continue to shape the course of science and human discovery for generations to come. In the grand scheme of the cosmos, life and death are the ultimate expressions of the universe's power. From the birth of stars to the creation of planets that can support life, from the growth of galaxies to the eventual death of stars in spectacular supernovae, the forces that govern life and death in the universe are both awe-inspiring and mysterious. These cosmic processes are not random. They are governed by the same fundamental forces we've discussed throughout this book: gravity, electromagnetism, and the strong and weak nuclear forces. Together, these forces dictate the cycles of creation and destruction that shape everything from the formation of galaxies to the birth and death of stars, planets, and ultimately life itself. In this final chapter, we will explore how the hidden forces of the universe shape the life cycle of stars and galaxies, the creation and destruction of matter, and even the potential for life to exist elsewhere in the cosmos. We will delve into the processes that give birth to stars and planets, how they live out their existence, and how they eventually die. We will also examine the role of death in the universe and why it is just as important as life. In the end, we'll discuss how these forces, the same ones that control the cosmos, might one day help answer the biggest question of all. Could life exist beyond Earth? The birth of stars. The forces. Behind star formation, stars are the lifeblood of the universe. They are the factories that produce the elements needed for life, the engines that power the universe, and the beacons that guide us through the vastness of space. The birth of a star is one of the most fundamental events in the universe, and it all begins with the force of gravity. Stars form from molecular clouds, vast regions of cold gas and dust in space. These clouds are made primarily of hydrogen, the simplest and most abundant element in the universe. Over time, gravity causes these clouds to collapse under their own weight, pulling the gas and dust particles together. As the material condenses, it begins to heat up, and the process of star formation begins. At the heart of this collapsing cloud, the temperature and pressure rise so high that nuclear fusion can begin. This process, driven by the strong nuclear force, occurs when hydrogen atoms are compressed and fused together, releasing an immense amount of energy. This energy, in the form of light and heat, creates a star. The forces that govern star formation are a delicate balance between gravity, which pulls the gas and dust together, and the pressure from the energy produced by nuclear fusion, which pushes outward. As long as these forces remain in equilibrium, the star will continue to shine. However, once the hydrogen fuel in a star's core begins to run out, the balance tips, and the star will begin to evolve into its next phase. The life of a star. How stars burn through fuel. Once a star is born, it enters its main sequence phase, during which it spends the majority of its life. During this phase, stars continue to burn hydrogen into helium through nuclear fusion. The strong nuclear force is responsible for fusing these atoms together, creating an enormous amount of energy that is radiated out as light and heat. This energy counteracts the gravitational pull that would otherwise cause the star to collapse in on itself, creating a stable, shining object. The life of a star depends on its mass. Smaller stars, like our Sun, burn through their hydrogen fuel slowly and can remain stable for billions of years. Larger stars burn through their fuel much more quickly and have much shorter lifespans, often only lasting a few million years. As stars burn through their hydrogen, they begin to fuse heavier elements in their cores. For example, once the hydrogen is exhausted, stars like the Sun will start to fuse helium into carbon and oxygen. This process continues with heavier elements, but eventually the star will run out of fuel. Without the energy from fusion to counteract gravity, the star will collapse under its own weight. The death of stars, supernovae, and black holes. The death of a star is just as dramatic and awe-inspiring as its birth. When a star exhausts its nuclear fuel, it can no longer sustain the fusion process that keeps it stable. The core contracts under gravity, becoming increasingly dense, while the outer layers expand, causing the star to enter a phase called a red giant or supergiant. In this phase, the star can become hundreds or even thousands of times larger than its original size. For stars that are not massive enough to become black holes, the death of the star is marked by a supernova, a violent explosion that occurs when the star's core collapses. During this explosion, the star sheds its outer layers into space, enriching the surrounding region with heavy elements like iron, nickel, and gold, which are crucial for the formation of new stars, planets, and even life. In the case of massive stars, the collapse of the core can result in the creation of a black hole. Black holes are regions of space where gravity is so intense that not even light can escape. They are the end state of the most massive stars, and their formation is governed by the force of gravity. When a star's core collapses to the point of singularity, the curvature of space-time becomes infinite, creating a black hole with an event horizon from which nothing can escape. Even in death, stars play a vital role in shaping the universe. The heavy elements produced during supernovae are scattered across space, eventually becoming the building blocks of new stars, planets, and galaxies. This cycle of creation and destruction is a fundamental part of the universe's ongoing evolution. The formation of planets. How gravity shapes worlds. While stars are the main engines of the universe, planets are the worlds that form around them. Planets, like stars, are born out of gravity, but the process of planet formation is somewhat different. When a star forms, it is often surrounded by a protoplanetary disk, a cloud of gas and dust that orbits the newly formed star. Over time, gravity causes particles within the disk to collide and stick together, forming larger bodies known as planetary embryos. These embryos continue to collide and grow, eventually forming planets. The force of gravity continues to play a crucial role in the evolution of planets. Once a planet forms, its gravity causes it to hold onto an atmosphere, which protects the planet from the harsh conditions of space. Gravity also dictates the planet's shape, pulling the material of the planet into a spherical shape over time. While the strong nuclear force powers the creation of elements in stars, the electromagnetic force governs the formation of chemical bonds that create planets and the complex molecules that make life possible. For planets like Earth, these forces combine to create the conditions for liquid water, a crucial element for life. However, planets are also subject to destruction. Through impacts from comets and asteroids, or the eventual death of their parent stars, planets can be destroyed. But this destruction is part of the continuous cycle of cosmic creation. The origin of life. How the universe supports life. Life, as we know it, is the product of complex interactions between matter, energy, and the fundamental forces of nature. But how does life arise from the elements that form planets and stars? The creation of life is still one of the greatest mysteries in science. However, we know that the right conditions must be met for life to form, and those conditions are created by the forces of nature. The electromagnetic force is responsible for creating chemical bonds between atoms and molecules, which is the foundation of all matter, including living organisms. Carbon, for example, is the fundamental building block of life on Earth because of its ability to form stable bonds with other atoms, creating the complex molecules needed for life, such as proteins, nucleic acids, and lipids. Gravity also plays an essential role in the formation of life. It influences the movement of liquids, like water, which is essential for life on Earth. Gravity also shapes the environment of planets, creating conditions that might be hospitable for life to develop. For instance, the Earth's position in the habitable zone of our solar system, the distance from the Sun that allows liquid water to exist, is a direct result of gravitational forces within our solar system. Death in the universe, the cycle of creation and destruction. While the forces of nature bring life into existence, they also have the power to bring about destruction. The death of stars, the collapse of galaxies, and the ultimate fate of the universe are all determined by the interplay of the fundamental forces. The universe is constantly undergoing a process of creation and destruction, and the forces that govern these processes shape the very nature of existence. The death of stars marks the end of their life cycles, but it is also the beginning of a new cycle. The heavy elements created in supernovae are spread throughout the universe, eventually forming new stars and planets. The death of a planet, or even the collapse of a galaxy, is part of the larger cosmic cycle. From the death of stars to the formation of black holes, these processes are essential for the evolution of the universe. Even life on Earth is not permanent. Life, like stars and planets, is subject to the forces of nature. The death of species, the eventual exhaustion of resources, and the changing of environments are all natural processes shaped by the forces that govern the cosmos. The potential for life beyond Earth. Are we alone? The forces of nature that support life on Earth may also play a role in the potential for life elsewhere in the universe. The discovery of exoplanets, planets that orbit stars outside our solar system, has opened up new possibilities for finding life elsewhere. Many of these exoplanets are located in the habitable zone of their stars, where conditions might allow liquid water to exist, making them potential candidates for supporting life. The question of whether life exists elsewhere in the universe is one of the most profound in science. As we continue to explore other planets and moons, such as Mars, Europa, and Enceladus, we may discover signs of life, or at least the conditions necessary for life to develop. The forces of nature that created life on Earth may be at work elsewhere in the cosmos, waiting for the right conditions to give rise to life. Conclusion: the forces of life and death in the universe. The universe is a vast and ever-changing place, and the forces that govern it, gravity, electromagnetism, and the strong and weak nuclear forces, shape the cycles of creation and destruction that define life and death. From the birth of stars to the formation of planets, from the creation of elements to the rise of life, these forces work in harmony to shape the universe. The forces that govern life and death are not isolated or separate, but are interconnected in a web of relationships that span the cosmos. Life, like stars and galaxies, is born from the fundamental forces, and death is an inevitable part of the cosmic cycle. The mystery of life and death and the forces that shape them is one of the most profound questions we can ask. As we continue to explore the universe, we may uncover new insights into the forces that govern creation and destruction, and perhaps one day find answers to the ultimate question: could life exist beyond Earth?